Oi, bio-inspired AI, integrating biological complexity into artificial intelligence. This is the latest Michael Levin paper. I'm sure if you're watching this video, you clicked it because of him. He is all over the internet, and I am totally going to abuse his face for a thumbnail. We're going to read his paper today and walk through it. Oh, 8 Rice, thank you for becoming a supporter. Appreciate that. Thank you so much. All right, to the paper. Biointelligence is not confined to neural systems. Research shows that even single-celled organisms exhibit information processing and adaptive behavior. So this is a very rare point to make in the paper is that we're currently using artificial neurons, which are meant to emulate biological neurons, but the reality is that in biology, information processing is done by more than just neurons. Every cell does info processing actually. For instance, paramecium, a eukaryotic unicellular xylates, whatever that means, a small single cell, can integrate sensory inputs and modify its behavior accordingly. Plants also demonstrate sophisticated behaviors like signal transduction and environmental responsiveness without a nervous system, challenging the traditional notions of cognition. This is crazy. So, I actually wasn't aware that plants did not have neurons. I mean, obviously they don't have like a spinal cord or a brain, but I kind of just would have, if you had asked me, I would have assumed they do. But I just don't know anything about plants, I guess. But yeah, you actually do not need neurons to do information processing. Neurons are cells that are specialized specifically and only for info processing, but really all cells do participate in some way, whether it be through hormone transmission or whatever it might be we'll get into soon. But in this paper, he's making a huge point as to the fact that currently our dynamic in AI is one of artificial neurons, and it might be the case, or might not be, that we need to integrate information processing of different forms in order to get the actual dynamic plasticity, uh, whatever that biology has. A path toward artificial neural intelligence involves not merely replicating neural architectures, but implementing the multi-scale, hierarchical organization found in life. In such systems, every level, from molecules to cells to organisms, possesses competencies and engages in adaptive information processing, a concept known as polycomputing. So here we're hitting the fact that they're hierarchical, right? In biology, we actually have systems where we have low level systems that do information processing, like the actual individual cells. Maybe you're like neural like receptors of your actual whatever taste buds or something, whatever it is. And then as you move up and up levels, those higher levels, it's kind of a hierarchy of intelligence of actual information processing, right? And that is something that you also do not see explicitly in the architectures of most current AI systems. You do see it implicitly in the actual arrangements of what the representations and everything happening inside these models. Like, for example, convolutions, you do end up with low level, like edge detectors and things in convolutional neural nets, and that those at higher levels create actual, like the concept of dog or something, right? You go from like edge detectors and curve detectors up to like I don't know, wheels and ears and paws up to like dogs and cars, right? So there is an emergent hierarchy of representations in our current AI models, but hierarchy is not actually built into the architecture in the way that it is in biological systems. And he's pointing out that it's not even just cells, even the individual molecules themselves, in a way, are input output machines, functions reacting to stimuli, right? In the case of like molecules, aka like proteins type things, right? And that when all of these systems at every level come together, we're calling it polycomputing. So I'm going to say bio instead of biological because I talk too fast. These biosystems often perform polycomputing, the ability of the same substrate to perform multiple computations simultaneously, right? So whereas with our current transformers and whatnot, right, there is one actual fundamental computation happen, which is just next token prediction, right? Everything else is in service to that one goal. Here in polycomputing, different pieces have different processes, different goals, different actual behaviors. Whereas, and like to some extent, you could say, I guess, that like they are all in the goal of like evolutionary fitness of survival, right? But like, not really. That's like quite a stretch in terms of that's more like akin to the actual gradients descent than it is to the actual next token prediction, right? Now, unlike traditional computers, living systems components carry out diverse functions concurrently. For example, a protein may participate in metabolism, signal transduction, and structural support. So one protein could be structurally holding the cell together, which is like a non-information processing function, and it can be doing metabolism, which is like a physical like also function as well, and it can be doing an actual um, information processing function, aka signal transduction, right? So like everything has multiple uses in biology, or usually. Future quantitative biological models must translate macroscopic goals into computational rules at network, unit, and intracellular scales. So what they're saying is like, um, in biology, we have our macroscopic goal of survive, right? And that this macroscopic goal has properly translated into computational rules, aka goals and like patterns at different scales, aka like the network as a whole, the entire human body, right? So then down to like organs, then down to individual tissues, then down to the units, aka cells here, and even below cells, intracellular scales, right? Is intra below and inside, or is it between cells? I think it's inside cells. Yeah. Um, and basically, like in biology, has figured out how to properly translate that macro goal of let's survive, all the way down to individual goals for each cell and for each protein in a cell, which is very interesting, right? Whereas in AI currently, we don't really have much in the way of we have nothing really in the way of purposeful lower level goals. We do have again emergent lower level functions and goals and things with like, oh, this one circuit is a curve detector, this one circuit is an induction circuit, that kind of thing, right? But those are all emergent from the actual gradient descent. Ours are in that way a bit less purposeful, and importantly, when I say like that in biology that they're more purposeful, like the one of them at a higher level changing isn't almost guaranteed to mess up a lower level piece, right? Whereas in artificial neural networks, currently what's happening is like if I were to change the actual uh loss function of the model, and the fact that the full thing is like fully interconnected means that the individual circuits, like the lower levels, like the induction circuit, for example, the induction head, would probably get messed up immediately. That like these smaller scales aren't have no sense of independence. They only exist like emergently. They don't actually have any unique siloed modular functions that they can maintain when goals move at the macro scale, right? Whereas in biology, it does. Conventional AI often seeks intelligence emergence from components lacking world models or goal directed behavior. In contrast, biology exhibits problem solving at every level, with behavior resulting from cooperation and mutual shaping of diverse modules across scales. So, whereas, like, again, like the gradients we use in artificial neural networks are like a top down forcing on everything else, in biology, it's more so a dance between the top levels and bottom levels. The bottom levels don't immediately say, "Oh yeah, sure, whatever you want, top level." Like your the protein in your cells does not go, "Oh sure, human brain, I'll do whatever you want." Like no, there's like a dance between them, mutual cooperation and shaping of diverse goals of these diverse modules, right? Whereas with our current transformers and whatnot, the gradient is in charge, the loss function is in charge, and the moment it changes, everything down below just gets screwed up. Hence, the issue of in continual learning fields of the forgetting issue of like the moment you keep training or change the actual training topic, you end up with um, just messing up with the smaller portions. Now, the problem here, strictly adhering to biological models risks overfitting. So another problem here, sorry, just to, a qualifier here is that we don't want to just strictly adhere to biology, right? To do that would be to risk overfitting. Instead, biology should inspire, not constrain AI design. This is why, like, don't get me wrong, I love when I see spiking neural networks and everything happening. But when people try and say, like, oh, this is the only way, I'm like, no, 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 no. If you can look at biology and see something cool, it inspires you, and you make it on silicon, and then you test it and it works well, great, I'll use it. But until that time, do not force me to go down your routes. The reality is, that it might be the case that optimal intelligence on a digital platform, aka like silicon like computers, right, might work very differently from the carbon substrate that we biology use, right? The difference in substrate, carbon being biology, silicon being digital computation AI, right? Means that probably not everything in biology is going to work very well in AI. And there might be some useful things, and there have been so far. Like neural networks in general are inspired by biology neurons, right? But they are not one-to-one copies. They are actually very different. We use floating point values. We have they are fully connected as opposed to sparsely connected, et cetera, right? There are big differences for sure. So again, biology, if you get something from it, it should be an inspiration that may or may not work. And if it does work, sure, let's use it. But by no means should anyone try and force us to use methods from biology in modern AI design. It's not a good idea to just like blindly follow biology when the actual substrate you're working on has fundamentally different properties, right? Now, here's something interesting. Biological systems do not operate on fixed instructions, but adaptively process information based on context. This is interesting. Is for a biological system, it is impossible to actually instantiate said system in a vacuum and try it on a new context because every new piece of data it receives is just adding to the context of everything it has experienced before, right? With a transformer or like a neural network or something, you can just wipe your key value cache and input a new prompt, and that is the only context the model now has, right? When you train an AI model, and a transformer, for example, you train it on different pieces of text on different documents, different internet web pages or whatever, entirely set that are all entirely separate and independent in terms of their context. Meaning that this model is like for each sequence in the training batch being instantiated and told to fit some loss function in that little micro context all separately and uniquely. It's almost like you are taking, if you were to take a person's brain and like pop it out of their body and put it in somebody else's head for 5 minutes at a time and keep moving it from person's head to person's head and ask it to learn when you're like flying it across the globe, putting it into somebody's different head entirely, different person, different job, different circumstance, different context, different culture, everything, right? Whereas in biology, the way learning happens is no, everything is in the same context. You can only add to the context and to some extent forget context based off what cannot be held in the brain and is less important and whatnot. So this is interesting to think like, okay, from can we be inspired by biology here? Would there be a way to train neural networks, transformers, for example, off of the context of the entire data set or something, as opposed to individual sequences of the internet kind of thing, right? Now, obviously, you can't take what I just said literally because you can't throw the entire data set in because that would be a batch size equivalent to the entire training data set, which is just computationally infeasible, right? But instead, can we find ways to provide more context what we currently have, right? An example of this might be so some early natural language processing papers used to use Wikipedia as a data set, right? They would show the model individual Wikipedia articles, again, all separately, effectively in the batch, right? And then they'd have the model try and predict the next word in that Wikipedia article, right? What if, and this is the thing that does happen, what if for every single on Wikipedia, you know, there's like links to Wikipedia, they have like links to other pages, right? What if for every single time the Wikipedia page linked to a different Wikipedia page, you actually allowed the model to not just view the current one, but also view that other page. So view the context of that other page, right? Are there ways to add more context to our actual training system? I do think this is a huge issue in AI and current GPTs and language modeling is that like we are training these things. The best we do so far is we'll take like, for example, in a GitHub repo, there is like 3 Python files in the repo, whereas we used to just train on each file individually. Now what you'll see with like, I think DeepSeek Coder might have done it, is they actually concatenated all three files into the same sequence and put tokens in between them, special tokens to denote new file starts here, new file starts here, so that now suddenly the actual model can learn from the context from all other files in that GitHub repo as opposed to just itself, right? That's super cool. And that gave, I believe, very, very good performance on code, which is great. But it's not quite perfect because like those three Python documents, right, might not have actually been written in that sequential order, especially when you have like many, many documents in your repo. It could be that like rather than having a sequential order, that some of those documents should be looked at in parallel, where they both have the same dependencies and they both have the same things dependent upon them, or something like an actual directed acyclic graph structure would probably be a lot better than what DeepSeek Coder did, right? In terms of actually managing context. But it's like, how do you put that into tensors? I don't know, right? That's the issue. And the thing here, like the inspiration to take is like, okay, for your next project, how can we think about putting these documents into the context within which they were actually originally made, right? That's a big question here. Like, for example, it would be great if when training on a history textbook, we could actually look at the context of all the primary sources, which with DeepSeek's attempt with their whole like put things into the context window just sequentially makes no sense because the context like this too long, even with like Gemini level 2 million token context length, it's still honestly computationally infeasible to take every single primary and secondary source that has been cited in that textbook and put it first, because like then it's also like, okay, do we just do one level or do we go back further and like for every source that the textbook cites, what about the sources that those papers cite, right? Like how do we actually make this happen? Of this, how do we create this like actual huge DAG type structure? I don't know. But if someone can figure that out, that'll be a huge, 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 like orders of magnitude improvements to actual performance in these models. In complex environments, organisms cannot rely on pre-computed optimal solutions. Instead, they employ heuristics derived from experience, particularly trial and error methods, to adapt to new challenges. This is speaking to the need for reinforcement learning, basically, and for honestly for much better reinforcement learning for like attempts that like what you see something like recently with what was the newest Google paper called? Was it Genie? I forget what it's called, but it's the one where they actually have like entire video game worlds simulated, right? What we need is the ability to create different counterfactual environments in which like, okay, but if you hadn't gone down that route, can we try something else? What would have happened instead, right? If you had turned right instead of turned left. Genie 2, thank you for that. Like something like that. The idea there with Genie 2 being, okay, now that we have this model that can simulate entire like worlds, right? So, like entire like video game worlds, then when we want to train a reinforcement learning agent within it, now suddenly, whereas with self-driving cars in the real world, all we have is data on the human turning right. We don't know what would have happened if the human had turned left, right? But once we have these simulations, the simulation worlds, now suddenly we can say, actually, let's run both. Let's turn right and turn left and compute what happens in both of them in parallel, right? And that would allow for kind of trial and error methods and reinforcement learning to be much more widespread and work much better, right? Now, of course, in real life, biology also can't do that, right? So instead, they employ heuristics derived from experience, right? And like, okay, I'm not super fond of Michael Levin and the other authors of their statement here, just because like, okay, what do you think transformers are doing other than applying heuristics? Like they don't actually like. Sometimes they have very good algorithms. Sometimes they are doing straight up stochastic parroting. The thing in between there I would call heuristics, right? Like I don't actually the point I don't see the actual point here what they're like critiquing. Um Obviously like yes, the model does have pre-computed optimal solutions to the extent that it has memorized some portions of the data set. Eight Rice asked, "Am I still considering GitHub repo as the input?" Sorry, I've moved way past the whole GitHub repo thing. We're talking about reinforcement learning in the context of simulations like Genie 2 right now. Um, Sorry, I jump around quite a bit. Um, but so most models nowadays don't actually rely on pre-computed optimal solutions, like in a memorization sense. They have moved into more, I would say, on average, the heuristic level. But their heuristics are definitely nowhere near as good as those between in biology, obviously. Where in biology we oftentimes have like full on, uh, not just heuristics from experience. At least in the human case, we can get full on like correct algorithms in some scenarios, right? Anyways, this approach enables effective exploration without exhaustive search, favoring adaptability over perfection. Yeah, we've already gotten the whole um this happening with, like, for example, the latest version of AlphaGo or whatever it was, I believe, or there's something where the best models no longer actually do exhaustive just depth or breadth first search. They are now doing a neural mechanism, which effectively you have to assume is using some kind of like heuristic, some kind of like statistics in that sense, right? So I don't see a huge point to this thing other than the call to action for reinforcement learning. The implication that AI models don't do this heuristics already is kind of silly to me. Similarly, chess masters use experience-based heuristics to focus on promising moves, navigating vast possibilities without calculating every option. Yeah, like we already have AIs that are now doing heuristic based, not actual breadth depth first search. How does a system exhibiting context dependent non local behavior remain stable? All right. So it's very easy when you have all these connections, like aka all this extensive context and the model itself having so many connections inside of itself. It's very easy for just a novel input to send signals throughout that just like ruin the stability of the system and send it off on an error prone tangent or whatever it is, or cause chaotic behavior, right? How do we create systems that do not exhibit chaotic behavior? To effectively control a system or adapt to an environment, the internal control mechanism must possess a variety at least equal to that of the system environment complex. This is interesting, right? So we have our given system or our environment that our model is working within, right? If we want to adapt to that environment, we need um, a complex enough model, aka a model with at least as much variety as a system itself. We need the model to be able to compute and create a simulation internally of what's happening out in the environment so that it can act accordingly. In order for a model to act effectively in its environment, it needs to be able to predict its environment, right? In order to predict its environment, it needs to be able to simulate its environment and play out that simulation in its own in its own head, right? So the model itself needs to be at least as complex as the environment. If your environment has some number of dimensions in it, right, in order to uh, work within it, you have to have its level of complexity. Now, not actually like fully its complexity level. Like obviously, I don't actually have to have a degree of freedom in the neurons in my brain for every single atom in the universe. Obviously, not nowhere near that extent, but like to the extent that like the vast majority, 99.9% of variation in my environment can be accounted for by some given d-dimensional pattern structure. My internal model is going to also need at least d dimensions to simulate that structure, and then as well like possibly more in order to make decisions accordingly, right? Eight Rice said seems like a chicken slash egg situation. um I think I kind of see the intuition there, but no, because the environment already exists. So the environment is the first thing, and then your model, we're just saying, needs to be a sufficient size, and then we can start training your model in that environment, right? So we need they're saying we need a model of sufficient size, right? Isn't this infinitely recursive? So because you don't actually need to model every single atom in the universe, no. the recursive thing, you might be asking about like, oh, modeling your environment, but you are in your environment, you model yourself. Yeah, so like a a progression of intelligence we have seen involves, okay, simple organisms um learn like maybe like cells like bacteria for example might learn one-to-one mappings of inputs to outputs, and by learn I mean evolution, genes, very barely even call it learning, right? And then um move up a level, like simple animals, right, do start to build world models. They do start to build some sense of like they start to build some sense of like computation of like, oh, we are going to simulate the worlds and act accordingly. What you'll notice is that there's a couple components that people call consciousness. The main one of the two main ones is self-awareness. What humans do is we said some thousands of years ago, whatever, we said, okay, we are already monkeys simulating our environment, right? We are becoming very social monkeys to the point where now the other monkeys are becoming important parts of our environment, right? Now we need to simulate the minds of the other monkeys, right? See how this gets weird right now? And then it moves to, okay, we can now simulate the minds of other monkeys a little bit. Like, oh, I can tell the other monkey is going to be happy when I give them when they get a fruit, right? But then you realize, wait a minute, the other monkeys are simulating us, right? They are also social animals. They have a simulation of us in their head, or of myself in their head, right? So in order to actually fully simulate them, I need to now simulate myself. I need to now be able to, in order to tell what they're thinking, I need to know what I'm thinking. I need to have an awareness of my own self, a self-awareness, right? That I can then use for theory of mind of in their minds, right? To account for what they think. I need to, in order to properly act in accordance to what you're doing, how you're going to act, and how you're thinking. I need to know what you think, and you're thinking about me. Therefore, I need to know about me. Therefore, I need to develop self awareness, right? So it's like it is kind of. It actually does keep going from there. We're not going to go up more levels, but it does go up more levels. It does get like infinitely recursive. Yes, you're right, but it's like a thing where as intelligence has progressed, so too has this infinite recursion of um simulation levels, to where you will notice some humans both throughout their life, like period, and just in a given moment, are simulating a different level, right? Some people are capable of comprehending, okay, not just my local community, and right, then they also do themselves, right? Then they do their like community's impression of themselves. Then they move up to, okay, but my community exists within the context of all of the other communities in the globe and whatnot, right? Like some people have gotten the ability to actually keep going with the infinite recursion of simulation of like of minds and of environments, aka like, and minds are your environments, to where they can now actually think in terms of like a global consciousness, right? So this is what you see with like how like in like a philosophy class you hear about morality, right? You hear like, oh, it's much easier to have empathy for someone who is close to you, your best friend, your parents, or whatever it is, right? When you move out to like your community, it's still pretty easy but harder, right? Move out to your acquaintances, it's pretty hard to like simulate what they're doing in their minds and have empathy for them and etc. Right? Move out to like people on the other side of the globe, someone like some other country, some other person, right? It's very difficult to actually simulate at that high of a level. And you're not actually simulating like exactly, obviously, you're not like thinking of like, you don't have a little version of all 7 billion people on the planet in your head, but you do simulate the globe in aggregate, like the global mindset, the average, or like the average and variance of mindsets, to where now like you see moral progressions of like um for example, I'm gonna try and avoid a little politics here, but like uh some so to do it we'll just not name names. Currently there's a world event. No, should I how should I avoid this? I don't want to talk about this topic. How can I avoid this? We're an AI channel, not a politics channel. Let's not talk the specific issue, let's talk the actual thing that's causing it. So Gen Z right now, TikTok is maybe getting banned, right? A big part of the reason is because Gen Z, banned in the United States, Gen Z is getting very anti-US government because they are, to an increasing degree, which started with MySpace but has been like accelerating with the higher level of connectedness with each new social network, and now TikTok's like a huge critical mass. As the level of connectedness, as the degree to which I hop on TikTok, odds are that I see a TikTok made by a 12-year-old in Sudan or something increases. uh those people become parts of our community, and we start to, through practice and through experience, gain the ability to actually have empathy for people across the globe. And then what you end up with is, when the whatever your local government um is doing something bad in a foreign place, now suddenly, unlike previous generations, you have a much easier time getting mad about that. Because even when you look back at like uh what was it, Vietnam Korean War, whatever, how the hippies were so mad about the war, they weren't really that, most of them, that mad about the whole like the foreigners that were being abused and genocided. They were mad about like, oh, the fact that they had to watch the actual images of like on the news of like the blood and gore, and more importantly like their own troops, our own like brothers and sisters, like I don't want to go get drafted kind of thing, right? They were still that sense. Whereas nowadays it's like Gen Z in America has no affiliation with a lot of these global conflicts happening and no actual connection to it. But because I, on the frequent, I watch videos of like teenagers, and I see that they're like house being destroyed by a bomb and like their like limbs being blown off kind of thing, like it expands that level of simulation of the environment. My environment is now becoming the whole world because of social media, and especially TikTok, because whereas previous social medias, like for example like Facebook, are like you just see your friends, right? Then it moves up to like Instagram. Okay, you just see a select number of influencers, right? And like same with YouTube. Right? Then it moves up to like TikTok. It's like no, no, no. Now you see everyone, because every single person on TikTok has at least one viral video. Is the thing, like almost everybody kind of thing. Like you see everyone. Anyways, that's a big tangent, but like that is the current process of like, yes, there is an infinitely recursive process here of simulating more and more of your environment, and as your environment becomes more and more people, you know have to simulate more and more people at higher and higher levels. And there is like a back and forth ping pong effect that I didn't really get into, of like self-awareness too, is like when you have to increase environment size, aka increase community size, increase like to the global level, whatever it is, now suddenly it's like, how does the globe see you? So like I am now not just self-aware in the sense of how do my family and friends see me, I am also self-aware in the sense of like, how does the world see someone in my demographic of straight white guy in the United States, in a rich place, right? Like there's a self-awareness of my own, not just individual brain, but also of my demographic, right? Like this, like it keeps going up and up levels. I think that's enough for that topic for now. I think let's move on. Eight Rice's next question. So how does biology set the line for when it's simulated enough details so that it can act? It's just an evolution, like a incentive structure thing. If you have no exposure to X level, X hierarchy of group, then you have no incentive structure to simulate it, right? And it used to happen in biology, but brains are effectively just speeding up evolution in a sense. Like we have software as opposed to hardware that we work on. Um, and so, and like medieval times, you would never meet people who were outside of your community, like outside of your 200-ish people in your village. You would never meet anybody outside of that. So there was no reason to go up a level past that. Whereas now it's like in 2024, I am interacting with people across the globe in some asocial way, or sometimes social way, on a daily. In my Discord server, people across the world talk to me, like in China and India and things. Same with this YouTube live stream right now, right? So it's about what environment level are you exposed to, and then like, is there any, once you are exposed to it, is there an incentive structure to act accordingly? Like, are you exposed in such a way that this increased awareness would be helpful, right? Like, if I was exposed in a way that was like, oh, propaganda being fed to me by my government and what's happening overseas, then like it wouldn't matter. In reality, like they're not going to show me anything like that like makes it advantageous for me to actually start like empathizing with those people, right? Like the my own government was never going to say like, oh yeah, these people who were abusing an ex foreign country, like here's some media to help you empathize with them, no, it's not gonna happen. They're gonna send me stuff that will actually like further 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 concretize whatever community level we're already acting in, right? Whereas if the environment I'm exposed to, if the actual people I'm exposed to, um, are doing so in such a way that like I am actually a part of the community with them, like actually interacting with them and getting exposed to their viewpoints, not just being told about them, then that's when I'll actually expand my level of awareness over time and over um, if I have the mental plasticity. You'll notice people who are um, there's a higher and higher chance as you get older, people do not have the mental plasticity to expand that level, even if they are exposed to the newer, larger group type thing. Okay, I think we're gonna move on past that topic a bit. Let's get back to the paper. Oh, the stability thing. However, simply increasing components and connections can lead to instability. Excessive connectivity causes chaotic dynamics. Some background on chaos if you don't know. Basically, some systems are boring, nothing happens. Some systems are somewhat boring, but things happen. Let's roughly call these periodic systems, where they just like do the same thing over and over again, very repetitive, right? Some systems exhibit what's called divergence, like they just like shoot off in one way and then they just effectively like it leaves the bounds of what we can think about, right? That's less so a thing with for example, divergence in the human body, like in the brain. If I had like a seizure so bad that it killed me, that would be like a case of divergence. Whereas periodicity, um, if I had like if I was very like oh, like when you get a song stuck in your head, that's an example of like some periodicity happening in your brain, right? Like your brain is a system, very complex system that like is having a loop that's like not wanting to like get rid of itself, right? Moving on to like chaotic dynamics, right? Uh, Chaotic in this context means it is not repetitive, it is not periodic, it is unpredictable, right? So somebody who is, uh, for example, schizophrenic, their brain is a bit too chaotic. It's going very all over the place. What you want in your brain is a little bit of chaos. Is you want enough that you are adaptable. You're not stuck in thought loops all the time. You're not stuck in a rut. You can actually like adapt to new things, but you don't want so much that you like can never do any periodicity because like the periodicness is useful for repeated tasks. Like whenever I go to eat food, I have eaten food many times before. I am using a periodic circuit that knows how to chew food. I don't have to relearn how to eat food every time, right? You need the ability in your brain to actually do um, that periodicity still. But you don't want so much chaos that you're like full on can't do anything, incomprehensible, going off on wild tangents 24/7, not able to take care of yourself, that kind of stuff, right? Now, when you have excessive connectivity, aka like your neurons are all connected. The output of every single neuron goes into the input of every single other neuron, right? Like there's just too many connections in your input output neurons, right? If there's too many connections, that will cause chaotic dynamics. Period. Like just too many connections, like it's just inevitable, especially if you have like if it's actually cyclic, that's the issue as well. Like that can create just crazy things start to happen in there. If you have not enough connections, then you can end up with the periodicity, right? Like if the just the whatever signal that's already traveling through keeps traveling through in a loop because it is isolated. There are not enough outside connections for it to change, right? It's like a wheel of like neurons, right? And like the thought loop is like stuck in like this cycle of neurons that just keeps moving through. And if there's no outside connections, if there's no connectivity, it'll just keep doing that forever, right? Whereas if there's too much outside connections, then that like signal will propagate elsewhere, everything else propagates in, and next thing you know, it's all going crazy. What you want is your loop, your wheel, to have some inputs and outputs, like a reasonable number, such that an important signal can come in and change the actual loop behavior, like the speed of it, maybe for example, or it can send signals out, type thing, right? Now, artificial neural networks, uh, assuming you were looking at like fully connected, just like regular, just like successive linear layers, right? They are fully connected but sequential, right? The worst case would be a fully connected and recurrent. That would be like it's just gonna keep chaotic going, everything, whatever, right? Um, what you have is something like a residual layer, for example. is like different modules. So there's less connectivity actually than like if you would take the same exact, if you were to remove all of the residual connections and just put every attention mechanism and MLP back to back. And if you were to um, make it single head attention as opposed to multi head attention, and you were to make it a regular feed forward network as opposed to the gated linear units, now suddenly you have like full connection. It's just not going to go, I promise you, aside from other issues like vanishing gradient, whatever, right? The connection is an issue, especially if you make it recurrent type thing. So biological systems address this challenge through modular organization, aka like we have an attention module, an MLP module for our transformer, right? Subsystems performing specific functions, maintaining stability while allowing complex behaviors, right? So when they need to do their function, they can do so. They can stay in their cyclic loop. My mouth can just chew and keep chewing and not have to worry about what the hell is happening in my brain right now that are my thoughts of whatever crazy stuff, right? Um, like if I had a fully connected brain, then every time I thought something, it would interrupt my mouth chewing and make it like do some other action, right? That'd be bad. So we get to maintain this stability while still allowing complex behaviors because when they need to, these separate circuits can then send signals to each other to change behavior of each other, right? 8 Rice said like a global set state. I am not a good enough programmer to know what that means. Apologies. Hierarchical structures facilitate renormalization processes, summarizing detailed, lower level information at higher levels to handle complexity effectively. Yeah, this is the thing where like why it might be useful to have a separate vision encoder, text encoder, etc. in your model is like um might be useful, right? Is then your higher level could just deal in semantics and your two little modules could like respectively deal with vision and with language, right? In the brain, you have different areas that are they don't like people overestimate the extent to which brain areas do something. Like your whole left brain, right brain thing is a bit like overplayed. All of your brain is always active when you're doing anything. Basically, like the whole thing is active, but certain areas light up especially hot when doing certain things. You have your Broca's area that does language, stuff like that, right? And so there's a hierarchy where like very low level structures will do very simple tasks, right? Like maybe like the individual pieces of the neurons in your eyes that like look at that like detect edges or curves or whatever, right? And then you can go up and up levels where like okay, your visual cortex puts all of those edges and curves and colors together into like actual reasonable objects that are somewhat useful. And then you're like prefrontal cortex interprets those objects what you're seeing and like makes decisions as to what should happen next meaning wise, and then it like sends commands back down to your spinal cord, which then distributes that rough command of like go of walk forward to like move right leg, move left leg, which then themselves split up into like tweak this muscle, stretch that muscle, pull this muscle, right? Like you have a hierarchical structure that allows each module to get the necessary info from all lower level pieces without overcomplicating it. Just get the necessary info and to communicate down to those lower level pieces and let them do their job without having to do it itself at the top level. A common thing I see with people, with humans, is that a lot of people, their higher level, so I call it their human brain, is taking too much control because in some cases it has the ability to take control from monkey brain, right? So monkey brain does, for example, many things, but for example, monkey brain controls your breathing rate. Maybe your average rate is like 30 breaths per minute or something, right? Your monkey brain, when you're not thinking about it, it's got it handled. It will control your breathing rate, right? But if you want to, you can take control of your breathing rate. Now that I've said this, you probably are doing it right now. You're probably thinking about it. You're probably sitting there going, you're very aware of your breath, right? What I see in people frequently is they oftentimes are using their highest level, their human brain, and trying to control too many lower level things and inevitably doing a worse job than monkey brain would do on its own, right? For example, if you go walk on gravel, I bet what you're going to do is you are going to look down at the grounds, you are going to look at each rock, you are going to a little bit think about, okay, what biggest rocks to avoid. You're going to think about where to place your foot and how to do so, and you're going to like scream and squirm and clench your feet very tightly and whatnot on this gravel, and you're going to walk very, very slowly and very painfully. What I do on gravel, which people find very, very interesting, when I go on hikes, people freak out at me. People freak out. When I go on hikes, gravel, rocky, I have hiked on places with volcanic rock, aka sharp rock, where you should not be hiking barefoot. Consistently, totally fine. I have like months spent hiking frequently, multiple times per week on sharp rocks. I hike barefoot. What I do is I do not look at the ground in front of me. I look up, I look ahead at the path way ahead of me. I let my peripheral vision implicitly look at the actual rocks and things in front of me. I let my monkey brain make decisions as to where exactly to step and how to flex my feet. And what it does is generally it's really good at avoiding things I should not be stepping on. It's so surprisingly good because I'm not thinking about it at all. It's doing it itself. It's like it is not stepping evenly. It is actually stepping like in an adaptive way. And all of the muscles of my feet are very, very relaxed as opposed to clenched. Because of this, I can hike miles barefoot in the colds on sharp lava rocks because your feet have so many muscles and bones in there, like in joints and things. Your feet, like people evolved walking barefoot. You can actually do this. It's a mental hurdle. In order to be able to do this, you have to be able to let go and let your lower levels of the hierarchy of your actual like computational brain neuron whatever systems that let your little monkey brain let it do its thing and think about something else. To do this, you have to not think about walking and the ground and rocks and pain the same way that you have to not think about a pink elephant in the class experiment. Do this right now. See for the next, pause the video and see if for the next 30 seconds you can avoid thinking about a pink elephant. Pause the video and try. I know you can't do it. You can't do it. There's like most people cannot actually avoid thinking about something. By trying to avoid thinking about it, you are going to inevitably think about it because you have no control of your highest level, right? And in order to do what I'm talking about with the whole monkey walk barefoot thing, you have to be good enough at meditating and stuff to be able to not think about the pink elephant, right? Once you can do that, you will be able to walk barefoot, right? And this what we're talking about is like the way your brain and your nervous system is supposed to work and be structured is that you are supposed to let lower level pieces do their job. But many people, much of the time, try and control those lower level pieces, and your uppermost brain, your human part of the brain, is just not made for that. It is made for like stories and metaphors and reasoning and like broad decision making and planning. It is not made for controlling the individual muscles in your feet and the positioning of your toes such that you don't get hurt when walking, right? And biology is very good at this. I highly recommend getting into this. Rob Newhouse said that they got to 11 seconds. What you'll also find, Rob, maybe you are actually good at this. Most people, when they start doing this kind of thing, they overestimate their skill in it. They think that they're doing it, when in reality, they are just so unaware of their own thoughts that they actually are thinking about said pink elephant. Like what they're doing in their head is they're sitting thinking, do not think about the pink elephant. Do not think of the pink elephant. Don't think about it. Do not think about it. Do not think about it. But they're actually like, by saying, do not think about the pink elephant, you actually are thinking about it. And it's not, that doesn't count. That doesn't count at all. Most people in this scenario overestimate their own skill at this. Generally speaking, you have to be like pretty good at meditation to get it going, which you might be. But like there's a classic story of this Buddhist retreat or whatever in India. There was one of these like oh, tech bros go to meditate for a week straight or something, right? And the what do they call them, yogis or whatever, the wise person they were all going to see, all these tech bros were going to see, was like, yes, what the hallmark of enlightenment is the ability to not think. By made for something, I mean evolved to do this thing. Your body evolved. So eight rice asked, "What do you mean our bodies are made for something?" Creationism, not creationism. I mean like, your body. I mean made to. I mean your body evolved. All these little sub circuits evolved to do their job, and your highest level, your human brain, also evolved. Rob, you meditate daily. Yeah, maybe you. Yeah, you're probably good. 11 seconds. I was. I don't mean to be doubt you, Rob. You probably got it. To answer eight Rice's question, um, your little subcircuits evolved to do their job, and also your highest level human decision making brain evolved to sometimes take over if necessary. And so it has the ability, but it is using that ability too often. It is like sometimes you need to have human brain take over because, for example, to hold your breath. Human brain needs to say, all right, monkey brain, stop breathing for me. I've got it now. I'm gonna do a few deep breaths, then hold it and go underwater, right? Because I need to go underwater for some reason, right? But people overuse this ability and tend to uh, take control from the subcircuits when they should not, basically, right? And so, not creationism, I mean evolution. It's just like your subcircuit evolved. Your feet know how to step if you let them. Also, with the feet thing, don't just meditate then start doing it. Chances are from years of what you using shoes, the muscles in your feet are atrophied, and the neurons in them are like dormant, whatever you call atrophy rate. So you actually, if you want to do this, if you want to start doing this, research first and start by walking barefoot on Bermuda grass. Then move on to regular grass on like soccer fields where you know it's safe to walk, and like slowly move up levels. Counterintuitively, pavements is one of the hardest things because if there's a rock, I guess like a single rock on pavement on a concrete on a flat surface, there is no way for your feet to actually move and contort and like avoid it. Whereas uneven surfaces are ideal, but you have to research, do it slowly, don't hurt yourself, right? So nice job, Rob, for meditating daily. I totally believe you got 11 seconds. That's awesome. Um, what were we saying? Oh, I was giving the story of the tech bros going to India for the dumb little retreats, right? For the to go see some yogi and meditate for a week straight, right? What happened? The yogi said something like a hallmark of enlightenment is the ability to not think, period. And maybe like when you do to like talk, just like direct thoughts to speech, like not have to like think through things or whatever, like, and to not have a loud mind, have a very silent mind. Like what's one sign of enlightenment? It's one like, I guess, a precursor to enlightenment. I guess I forget what the way they phrased it, but what happened during this retreat is, and like the yogi was like, oh, and yes, and like the enlightened one, the Buddha or whatever, or something like that, in theory, like would never ever think, would have no need for thinking or something like that. They were phrasing it weirdly. And then on this retreat, some white lady, of course, goes, well, I haven't thought this entire time being here. I haven't thought in ages. And they also like worshiping her, but like she was thinking the whole time. She's just so damn like self unaware that she like was being an idiot basically and like calling herself the Buddha as you know the white savior complex and whatever, right? Um, so like it's very easy to think, this is the whole pink elephant thing. It's very easy to think that you passed 11 seconds of not thinking of the pink elephant when actually you haven't. And Rob, I believe, has because he said he meditates daily. You meditate daily, I believe it. If someone who like didn't meditate at all said 11 seconds, I'd be like, no shot, no shot. But meditating daily, 11 seconds, that checks out. That checks out. Anyways, back to the paper, right? Importantly, hierarchical organization provides modularity, aiding in repair and improvement without disrupting the entire system. Okay, back to the hierarchy modules thing. Currently, with AI models, when we try and train them on a new thing or just continually train them, what happens, that's called continual learning. What happens is we have this issue called, is it continual forgetting or something forgetting? Anyways, when you keep training a model, it will forget what it previously learned. Because when you provide a training signal, what you're doing is you are changing the entire network because you're doing a global gradient, right? And the problem with that is that the result is that whatever piece of the network was doing said circuit now is forced to change and therefore gets broken. Whereas in biology, when we learn, individual modules have to change, get to change at a time. Whenever I need to learn something new, I am not requiring every single brain cell and every single like a central nervous system cell and every single individual body cell with its hormone learning process and every single molecule whatever to change. I am only requiring the parts necessary to change and therefore learn, right? Somewhat whatever, like if I'm learning like a new thing in language, it's like just my Broca's area that does most of the actual changing. Maybe a couple areas connected to it also change slightly in comparison, right? So that's a big question in continual learning and AI and stuff is how do we get the models to not only be more modular, but also learn in a more modular manner. And a paper recently that I read the abstract of, I'm going to read it soon. What they did was they said, hey, let's do continual training. Let's train a model that's already been trained, like keep training like a new task or something. But let's only actually edit the parameters that have the highest gradient norm, that have the largest gradient direction. Everything else, let's keep it the same. So they have some threshold where like if the gradient norm of this vector or whatever is above a given level, then we include it in our actual parameter dot step, right? If it's not, then we don't include it. What they found was that this, at least in the abstract, we'll see, that it massively helped with continual forgetting. I would love to see a training process in um, in just actual pre-training that takes advantage of this and says like, okay, how can we only train local bits at a given time, local parameters, as opposed to the whole global gradient thing right now. That'd be a good thing to do. Is I highly recommend if you want to experiment, is test that out and see like, okay, can I backprop my gradients, and then can I check the gradient norms or just the gradient values every given parameter or vector or whatever it might be, and set a given threshold of like just the top 10% of them, only them perform the gradient dot step on or the parameter dot step on, and then go. That'd be a very cool paper to see. The embodied Turing test proposes evaluating AI based on its ability to interact physically and adaptively with the world rather than solely through disembodied tasks like language processing or game playing. The idea of like, yeah, embodiment being crucial to actual long-term flexible learning has been a thing for a while. To a certain extent, I'd say like any environment you are like any data itself is an environment the model's embodied in. I think it's kind of silly. But to get what we want, which is learning applicable to human behavior and robots and whatever, yes, you got to embody the thing, right? So yeah, it's reasonable to think like you can't actually expect language models to fully develop a complete coherent model of the world based off just language, because in our language we only communicate information that is peculiar and non-obvious and therefore worth communicating, right? So they have developed very good models of things that we discuss in language, like code, for example. They're very surprisingly good at code, right? But at the same time, we in most uses of code don't actually discuss the specifics of the assembly or like below that, right? And because of that, a lot of the time in code they're using heuristics, not actual stuff, right? Or for example, not even code. Let's just say if you ask a model a question, I know the that okay, question by 8rice, but in the digital space, there's language, videos, and all sorts of 3D models of the world. Yes, so that's the thing is like 2 years ago plus, we really hadn't done a whole lot of multimodality, and so everyone was saying like, oh, we need to embody this stuff. I think it was Google's Palm models that were the first to like really show how cool embodiment was and how it improved the model itself, right? Yes, embodiment's great, right? So then when you implement like language, videos, 3D models, etc., like more modalities, exactly that's what they're saying is they're saying we need these things, right? However, there is still an issue of like agentic embodiment versus just having the modality embodiment, right? Um, a security camera footage that's getting piped into a multimodal language model is going to help the model develop a model of some parts of what it sees, of like the things happening in the security camera footage over time, right? Like it'll develop models of intruders and passersby and whatever, right? But there's a difference between that and what it's incentivized to learn there versus what it'd be incentivized to learn if it were actually put in a robot body and given the ability to move around and interact with the environment, right? It's a very like different incentive structure as to what it will learn. So to a certain extent, any data set can be like, whenever you're training on it, you are embodying the model in that data set. It's just we need more data sets, aka multimodal, aka yes, videos, 3D, whatever the heck, right? But then we also need agentic embodiment, the ability to act within that, right? So like, for example, we have currently O1 preview, now it's O1, right? It's reinforcement learning in the language model, right? That has been given an agentic embodiment in text because it's agentic, it's reinforcement learning, right? It is actually like choosing what to do 1,000 different runs. They choose the best run, then they train it off of just its best run, and therefore you get the O1 model, right? Stuff like that. Um, or for example, I'm gonna go ahead and share this because he told me, and therefore it's okay to share, I think, and because like O1's already out and stuff, and this is the next version, I guess. I was talking with a researcher at OpenAI. I'm pretty sure I can share this. I'm pretty sure because he told me, and the rest of the conversation, he was frequently not telling me things. He was frequently saying, "I can't share that with you because it's like we're doing it in house, close, whatever." Right? This I think is shareable. A thing they were doing is uh for, I don't think it was with O1, maybe it's the next version, maybe it is O1, I'm not quite sure, but they were giving the model an actual code interpreter, like a whole on, like, here's the import packages, here's the problem, here's the all the documentation, and here is the actual um you can run the script, right? And then they were letting it run those 1,000 times and letting it see the output of its own script and letting it like choose which did better, which did worse, and like and actually act within that context of now it's in an environment where its actions change the results of running said script and packages, whatever, and then it can, and then they use that to accordingly get training signals by having the model itself rate which ones were good training signals, which ones were not, type thing, right? They were and through this, apparently, when you run this on like a bunch of different languages and packages and stuff, apparently he said he's pretty damn confident that some later version of the model, maybe O2 or something, will be like, just for a fact, doesn't need to see documentation anymore or whatever, like just knows how to code in this language, period, and knows how to do whatever. Now that's still the open question of like large scale complex engineering. That's a whole separate thing because that depends on the actual question data set they're using. But in theory, anyways, huge step up incoming, right? It emphasizes building systems that can sense, act, and adapt to their environments. What I just said, agentic, right? Brain compromises roughly 2% of the body weight, but it utilizes 20% of the body's energy intake. Despite the significant energy use relative to its size, the brain is remarkably energy efficient compared to traditional computing models, um, consuming only about 20 watts of power with approximately 100 billion neurons with 10 to the 15 synapses firing at 1 hertz. This is wild. I've heard different approximations on numbers of neurons and hertz and whatever, but 20 watts of power, for context, I looked it up before this video. The new M4 Mac Mini uses on Reddit, it said, this guy said that they were doing I think I want to say it was like a video export or something, 22 watts under peak load. That was for video exporting, I believe. I forget exactly. So the brain uses about as much energy as an M4 Mac Mini under load, which is wild. Evolution incrementally added complexity to existing regulatory, intracellular, and neural structures, enabling advanced cognitive abilities while maintaining functionality. So we had these modules, and evolution incrementally improved each of these modules, and I guess occasionally, obviously, also had to add modules. In AI development, an incremental approach can mirror this evolutionary path, beginning with the basic sensory motor systems and gradually adding complexity allows manageable progress, right? This would be super interesting. Like, they're basically proposing, like, okay, what if you started off with like models that just do each modality and combine them, and then like added a thing on top, and then encouraged increased complexity from there and kept going up levels, right? That's what they're saying that we should do. What does that look like? Maybe like a vector autoencoder on the bottom at the lowest level for like one for text and one for vision and one for audio, etc., right? And then like maybe next token prediction of those vector autoencoder embeddings above that could be a way to do that. And then maybe like you have your next next embedding prediction, next encoding prediction, right? Maybe you diffuse a loose version of those or over those at a higher level, similar to that paper I read, might be 2 months ago now. There was like a diffusion language model that was whatever. But I believe that is it for this paper, right? No, no, we're not done. Comprising a substantial portion of brain cells, 50 to 90%, astrocytes interact extensively with numerous synapses. So these astrocytes, they are cells that are not neurons, and they compose most of the brain, and they interact extensively with regular brain cell synapses and with other astrocytes. And it seems like they are serving as integrators in spatiotemporal signaling. So whereas the neurons are moving in one direction, the astrocytes kind of on these many parallel neuron pathways, the astrocytes make communication between those parallel. Am I in front of the camera right now? Those parallel pathways, right? And some prior paper posits that astrocytes implement functions analogous to the self-attention mechanism in transformers, influencing information flow based on context. Very, very cool stuff. And that would be it. End of video. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.